Hi everyone, my name is Qasim and I'll be presenting our work on hardware SYN attack protection for high-performance load balancers. In Layer 4 load balancing, the load balancer is responsible for distributing the traffic across the servers. Each cloud service is represented with a virtual IP, VIP, and each server is identified with a direct IP, DIP. To design such a load balancer, we have three main challenges. The first one is performance. We need to support a high arrival rate of 1 million connections per second and up to 100 million simultaneous active connections. The second challenge is PCC, per connection consistency. This means that the load balancer must ensure a consistent connection mapping, even under a high pull-up date rate of up to 1 server per second. The third challenge is protection. The load balancer must be able to fight against a high SYN attack rate and mitigate its effect. A basic hardware load balancer can be implemented as the following. We have a hardware table called the ECMP and holds all the available DIPs in the pool of servers. Each packet coming to the load balancer will choose a destination DIP from the ECMP according to the hash of its 5-tuple headers, modulo the size of the ECMP. This solution works well in case the ECMP does not change and stays constant all the time. But since the ECMP would constantly change in today's load balancers, this simple solution wouldn't work, and the exact mappings of connections must be tracked. To forward the traffic correctly, the load balancer tracks the states of connections. In the connection establishment, the load balancer will learn the SYN1 packet coming from the clients and the SYN2 packets replied by the servers. Then it will understand that this connection has been established. Later, the client will start sending the traffic, and we call the first ACK as ACK3. When the client decides to close the connection, it will send a FIN1 packet. The server will reply with a FIN2 packet, which upon arriving to the client will close the connection safely. The load balancer will learn these two packets of FIN1 and FIN2 and will understand that the connection state can be discarded. Per connection consistency is an important aspect in load balancers. Let's say that we have 8 DIPs in the pool of servers. The SYN1 packet is forwarded to DIP 2 according to the hash of the headers. Later, a pull update happens, which takes down DIP 2 and replaces it with DIP 9. All the following packets for this connection will be misforwarded to DIP 9, causing the connection to break. To prevent this from happening, load balancers maintain actual connection mappings and use them to forward the traffic correctly. In our previous work, we designed a load balancer called Prism. Prism forwards all packets by hardware, even during pull updates and while ensuring PCC all the time. The main unique property in Prism is that it only maintains hardware mapping for connections affected by the pull update, and not for all connections as done in other load balancers. We call the table which holds these mappings as the Migrated Connections Table, the MCT. To ensure PCC during pull updates, Prism uses a special iterative algorithm where we copy all affected mappings into the MCT and prevent any connection from breaking. Prism's hardware packet flow looks like this. Each packet coming to the load balancer is first checked if it's a special packet of type SYN, FIN, or reset. If this is the case, we forward it through a hardware table called the FIB, which is responsible for learning the signatures of the connection. Afterwards, the packet is forwarded through the MCT table. which has all the mappings for the migrated connections which was affected by the pool update. If this is the case, the packet will find the mapping here in the MCT table and will be forwarded correctly. Otherwise, the mapping will be chosen according to the hash of the headers from the ECMP table, which holds all the available dips from the pool of servers. In Prism, the software is responsible for tracking the full states of the connections. These states are held in the Software Connection Table, the SCT. The software will periodically fetch the Feb learning tables and insert, update, or remove entries from the SCT table accordingly. Protecting load balancers against SYN attack is our main focus in the paper. In SYN Flood Attack, the attacker sends many spoofed SYN packets in order to make the server unresponsive and even crash. Servers have limited resources for half-open connections. Therefore, after some time, they will start dropping real new connections. Load balancers are also susceptible to SYN attacks. Since load balancers have limited hardware resources, similarly to the servers, they will be flooded with SYNs and will not be able to serve new real connections and probably crash. Moreover, the load balancer will not receive FIM packets for the fake SYNs, making it maintain fake states for a very long time. Now we present our first basic scheme for protecting the load balancer against SYN attack. Scheme 1. In this scheme, the load balancer will also learn reset packets coming from the servers and will discard fake connection states accordingly. These reset packets are sent from the servers after a half-open connection has timeout. This scheme has three main issues. The first one is poor performance. In this scheme, we will not be able to fight against an attack of more than 1 million per second. The second issue is that even to mitigate this attack, we will have to increase our hardware resources. This is something that we are not interested to do or not always possible. The third main issue is that this scheme does not work if the servers use SYN cookies. SYN cookies is a mechanism the servers use to protect themselves against SYN attack. In this mechanism, the server does not create a state for SYN packets, but responds with a special initial sequence number, called the SYN cookie. This number is generated using a hash function and a cryptographic secret key. Later, when the server receives an ACK packet with an acknowledgement number which equals the SYN cookie plus 1, then it will establish the connection. This is always the first ACK of the connection, which we previously called ACK3. We now introduce the main idea in our paper, using a hardware table to validate connections. We call it the Cookie Hardware Table, the CHT, and it stores SYN cookies coming from the server. The validation is done on ACK packets coming from the clients, where we check for a match for their acknowledgement number in the CHT. And only if there is a match, the hardware will learn the signature of the packet. The CHT will hold the SYN cookies for a short amount of time, of about round-trip time. This will enable real connections to be learned correctly, and will also enable a CHT to discard cookie values of fake SYNs very fast. In the paper, we present mathematical analysis and show that the CHT works correctly even under a high rate of SYN packets, and a false positive learning is very rare. We call the hardware flow which uses the CHT to validate connections as procedure 2A. In this flow, SYN1 packets coming from the clients are not learned in the FIB and just forwarded directly to the servers. This means that SYN1 learning mechanism is not affected by the SYN attack. SYN2 packets coming from the servers first pass through the CHT table to learn their SYN cookie. then are forwarded to the clients. The CHD actually learns the SYN cookie value +1, and later for ACK packets, the hardware will simply check for a match for their acknowledgement number. The hardware flow for ACK packets looks like this. The packet first passed through the CHD table to do the validation and check for a match of its acknowledgement number. If there's a hit, this means that this is an ACK3 packet, and the hardware learns its signature in the new fib of ACK3 packet. Then the packet is forwarded according to the MCT and ECMP tables, similarly to the previous load balancer flow. Procedure 2A may violate PCC upon pull updates. Let's take an example. Let's say that the load balancer forwards SYN1 packet to the server DIP1. DIP1 responds with a SYN2 packet which has a SYN cookie. Let's say that a pull update happens which adds a new server, DIP3. Later, when the ACK3 packet for this connection comes, the load balancer will forward it according to the hash of the headers to DIP3. Because the load balancer does not have any mapping for this connection, DIP3 will simply discard this packet, and the connection will break. We now present procedure 2B. This procedure is very similar to procedure 2A, but will also maintain PCC. This procedure uses the same CHT hardware flow for validating ACK packets and learning ACK3 signatures. The only difference is that we now get back to learn SYN1 packets to be able to maintain PCC. In this procedure, if a connection does not receive an ACK3 signature within round trip time, it will be considered as fake and will be discarded. This means that fake connections that are learned by the fib will be discarded very fast. The main drawback in procedure 2B is that the load balancer always needs to use the fib of SYN1 learning table, which considerably limits the attack rate that can be mitigated. As we discussed earlier, the fib of SYN1 table will not be able to maintain a SYN attack rate of more than 1 million per second. We now introduce the main scheme in our paper, Scheme 2, which puts together all the ideas we presented so far. This scheme will work when the load balancer detects that a SYN attack is happening. Otherwise, we will use the basic scheme, Scheme 1, which is simpler and works correctly while no attack is happening. The main idea in Scheme 2 is that we will use the fib of SYN1 learning table only during pull updates. In Scheme 2, most of the time we will run procedure 2A, which works correctly while no update is happening and maintains PCC, and only when a pull update is triggered, we will move to using procedure 2B, which will continue to ensure PCC. This means that the Scheme 1 will always maintain PCC without needing to use the fib of SYN1 learning table during all of the running time. Scheme 2 invokes procedure 2A per bin during a pull update. This means that upon each bin update, we will configure the fib of SYN1 to learn only packets forwarded by the currently updated bin. This is enough to ensure PCC, because we will catch all the signatures of connections which are in danger of breaking. If a bin finishes to update, then all of its mappings are safe and will not break. This will enable Scheme 2 to overcome the fib of SYN1 overhead. because we only need a small table now. The only overhead left is the size of the CHT table. Therefore, Scheme 2 will be able to mitigate an attack of up to 10 million per second. This number is integrated from how much cookies the CHT can hold simultaneously. In the paper, we presented a proof of concept prototype. In this POC, we implemented Scheme 2 CHT learning mechanism and used it to filter fake SYN packets. The implementation was done on a spectrum switch in P4 programmable pipeline for defining the new hardware flow. In the first pipeline stage, we trigger the CHT to check for a match for the ACK packet, or learn the cookie of a SYN2 packet. In the second pipeline stage, we trap ACK packets to the CPU in case it found a match in the CHT. Trapping this ACK packet to the CPU enables us to check that the validation was done correctly. Our test topology looks like this. We used a spectrum switch running the Sonic operating system for connecting the server and the clients. From the left side, we have a host which emulates the server. The server runs the Moongen traffic generator to reply for a high rate of SYN packets with SYN ACK packets. From the right side, we have the clients. The first one is the attacker, which also runs the Moongen high traffic generator to generate a high rate of fake SYNs. The real client runs a normal TCP three-way handshake from a Python script. In the first experiment, we made the attacker generate a SYN attack rate of 5 to 7 megapackets per second. To verify that everything is working well, we captured ACK packets learned by the switch CPU and ACK3 packets sent by the client. In the first graph, we see the captured ACK numbers throughout the system running time. We see that the switch only learned correct packets sent by the real clients. In the second graph, we see that the CPU usage throughout the system running time stayed very stable, even under the high attack rate of up to 7 megapackets per second. In the second experiment, we wanted to test the scalability of the system. We made the server emulate replying to a client's rate of 1 megapackets per second by sending random SYN ACK packets of 1 megapackets per second. We made the client side send random ACK packets of the maximum flow to emulate sending high real traffic without establishing connections. These ACK packets are non-ACK3 packets which are not supposed to establish a connection. In the graph, we see that a 40 million ACK packets was passing through the load balancer per second, and about 1 million SYN ACK packets was passing through the load balancer per second. We also see that the CPU usage throughout the system running time of 30 minutes was very stable, meaning that the CPU was not affected by the high rate of validation of ACK packets in the hardware. In our CPU logs, we didn't see any learned ACK packet, meaning that the CHT validation mechanism worked correctly and did not learn any ACK packet by mistake. In conclusion, in our work, we proposed a hardware-based scheme which takes advantage of a new cookie hardware table, the CHT, to protect load balancers against SYN flood attacks of up to 10 million per second. The proposed load balancer scheme can support a high connection rate of 1 million per second, together with a frequent pull update rate of 1 server per second, and without being affected of SYN attacks of up to 10 million per second. Thank you for listening.
Okay, thank you, Qasim. There you are, great. I would encourage anybody in the audience to post questions to Slack. I'll start off and try to start the discussion with a couple of questions of my own. The first question I had is, did you encounter any, what I'm going to call false negatives in your test, meaning that you have a legitimate a legitimate connection that gets dropped because you're aggressively trying to protect against malicious connections?
So yeah, in the experiments we did, like with 14 million packets of ACKs and up to 7 million mega packets of attacks, we did not see any like real connection drop. In the paper, we also had the yeah, so they are like real connections have to be learned. What we was afraid about is that fake connections might be learned, but we also didn't see this in the experiments with the rate we experimented on, and in the theoretical analysis, we also show that it's very, very rare, almost never happens.
Okay. Let's see, we're still not getting questions. I still don't see any questions in Slack, so I'll try another one here. So for your experiments you constructed this proof of concept based on an FPGA implementation. So going forward with existing load balancers, do you have an idea of how you would integrate your approach into those load balancers? Would they need hardware upgrades or?
Yeah, so we basically worked on the POC with NVIDIA. I worked with an engineer from NVIDIA, so we combined between the P4 and their hardware, which is like it's in the hardware, but like we can configure it somehow from P4. It's not like very generic, but it can be like configured from P4. So we actually used an NVIDIA built hardware table, the MCT, which I'm not like sure if it's like publicly can be like configured with anyone who buys the switch. I'm not totally sure, but with any like hardware table which has the match, which can match like signature with a high rate, it can like we can implement the same stuff we did. So yeah, the implementation is supposed to work on the any off-the-shelf programmable switch, but it's not guaranteed to have the results we showed, because the table itself need to be very efficient and able to handle the 1 million rate of connections.
Okay. So we have a question from the audience. It says, dropping Act 3s after a single RTT seems odd. Is the system totally predictable in terms of delay, or does the RTT time have some added headroom to prevent early drops?
Yeah, so the hardware table has the cookie connection table has timers in the hardware. It's basically like if a new connection, if a new signature, a new cookie comes with the same signature, it will overwrite
another one if the timer is like above round trip time. It's like a hardware mechanism to make sure that we don't like clear connections or clear entries very early. So we didn't like see this as an issue. We don't really drop connections very fast. It's like the main like the main talk about the round trip time is for more for like the analysis part, because it really affects the size of the CHT and therefore the rate of mitigation. So if you like want to increase the round trip time to say that let's keep cookies for more time, you won't be able to mitigate a high attack rate of when you pick a smaller or shorter round trip time. So that's the trade-off between the things. We do not actually like just drop connections before they are actually established.
Okay, sounds good. So I would encourage you to monitor the Slack channel. It doesn't look like we have any questions there, but if people have questions after the presentation, if you could kind of keep an eye on what's going on there and you can answer questions as they come in, that would be great. Thank you very much for a really interesting presentation. And that brings us to the end of this particular session. I believe that we're headed to lunch now, and we will resume, let's see, at 1:30 Pacific. Sorry,